it's great that you're economic, because the only way that decarbonisation is going to happen is if it saves money. And it's very sad that we're in that position, but it's true. And it does need to be economic. That needs to be a focus.
If you've been following Wicked Problems for a while, you will have been familiar with the Series 3, which is all about green tech. And a large focus of that was on EV, but there were other technologies in there as well. And part of the reason I did that is because I think there's a real benefit for UK organisations to really grasp the green revolution as a sort of new industrial revolution. There's so much innovation, and we're so good at innovation in the UK. And what we also need to be good at is execution of the innovation that we create in that green space. There's so much profit we can make from it, both here and across the world. I met with Dr. Harriet Kildahl. She's from a company called Perocycle. Now, Harriet's a chemical engineer and an entrepreneur known for doing pioneering work in industrial decarbonisation. She's also the CTO and co-founder of Perocycle. Perocycle are a deep tech spin-out from the University of Birmingham, and they focus on eliminating global industrial emissions in a closed loop system. So what that means is they're focusing, for example, right now on steel, and steel produces a lot of carbon dioxide, but it also requires carbon monoxide and oxygen. And so they split the CO2 into those component parts and reuse it, and then it formulates back into CO2 and round the loop it goes. She can explain that much better than I can. So take a listen. And at the end of this, if you're interested in learning more, I'd really encourage you to follow the links, check out Perocycle and the work that they're doing, because I think it's an excellent example of innovation in green tech. Harriet, welcome to Wicked Problems. It's really great to have you here.
Thank you so much for having me. Looking forward to having a good chat. Really
excited to learn about Perocycle, because anything that is helping to, reduce the carbon footprint of emissions I think is really interesting, at least for this show. Tell me more about, and tell our listeners and viewers more about Perocycle and what it does.
So Perocycle is currently an early stage climate startup. What we're trying to do is essentially decarbonize heavy industry. And we're particularly focused on, for example, the steel industry, where fossil fuels are used not only as energy, but also as a kind of carbon source for the chemical processes that are happening. And so what we're aiming to do is create essentially a closed carbon loop. So it means we take emissions out of a furnace, convert them into what we call carbon monoxide, and then put them back in the furnace. It's maybe useful to maybe give a little bit of context about how steel works, because I think a lot of people, steel is everywhere in our lives, but no one's actually really stopped to think how it's made, how it works. So there's two main types of kind of virgin steel making. You've got a blast furnace, where there's around, 1,700 blast furnaces globally. And then there's the slightly newer direct reduced iron, where there's less, but kind of they're the new generation of kind of steel assets, where more of them are currently being built. And in a blast furnace, the kind of carbon and the emissions comes from coal and coke. And what happens basically is you mix iron ore, so the iron that you kind of mine out the ground, you mix it with coke and sometimes some like pulverized, so like dust of coal. And in the furnace, it gets really, really hot. And as the iron ore moves down, it basically gets reduced. So that just means we take the oxygen out of the iron ore and basically make metallic iron. And the way that happens is the coke actually reacts with oxygen and forms carbon monoxide. So carbon monoxide is what we call a really good reducing agent. And so that's why with Perocycle, we want to make carbon monoxide, because we can inject that into the furnace. It reduces the iron ore into that metallic iron that we're looking for. And it means that we can displace the amount of coal and coke used in a blast furnace. In DRI, it's actually even slightly easier. So DRI currently uses natural gas, and the natural gas is reformed. It basically means it's split, and you get a mix of carbon monoxide and hydrogen. And those are both good reducing agents. Same thing, you put the iron ore in, gets reduced. And so therefore, by injecting carbon monoxide that we've made, we can reduce the amount of natural gas that's needed. And the reason that our process is circular is because when that carbon monoxide reacts with the iron in the furnace, it makes more carbon dioxide. So we take that carbon dioxide at the top We convert it into carbon monoxide, re-inject that back into the furnace. It reduces more iron ore, makes more carbon dioxide, and the circle essentially goes round and round with only the addition of heat.
And the heat is how you break the carbon dioxide, presumably into carbon monoxide and carbon.
Yeah, so actually it's what we use as a catalyst that's a thermochemical material. So it just means that chemical reactions happen as a result of changes in temperature. And so the catalyst basically has two steps. So we've got the carbon dioxide splitting step. And in that, the catalyst basically tries to steal an oxygen from the carbon dioxide, and you're left with then carbon monoxide. So CO2 to CO, stealing the oxygen. Then the catalyst is regenerated in a separate step where we basically just pass nitrogen over it, so a low oxygen atmosphere, and the catalyst then releases that extra oxygen that it had gained during the carbon dioxide splitting step. And you basically reform the active catalyst, put carbon dioxide back over it, make more carbon monoxide, regenerate the catalyst. So you've kind of got two loops going on. The catalyst has got its own little loop, and then in the steel furnace, you've got the carbon dioxide loop as well.
So carbon dioxide, you steal the oxygen from that. Where does that oxygen go? Do you need to provide more oxygen later, or is it just it's part of the loop as well?
Yeah, so the oxygen kind of gets absorbed into the structure of the catalyst. So the catalyst basically has these little holes, and then when it sees the carbon dioxide, it wants to fill that hole that it's got, and it wants to fill it with oxygen. So it grabs the oxygen, fills the hole, and then in that reduction step, so when we put the nitrogen, that's when it then releases that spare oxygen. So we get a mix of nitrogen and oxygen as kind of our waste gas, which obviously can just be vented, and you end up with that hole again with the catalyst wanting to refill it with oxygen.
What's the plan in rolling this out? Are you already in places already, or is it you're just launching, or whereabouts are you in your journey?
Yeah, so I'd say we're relatively early stage. We are currently putting the final steps on a 100 kilo catalyst reactor. So not lab scale anymore. We're kind of like in a container-sized unit, and that will be running now indefinitely, that we can start to understand kind of catalyst lifetime better. And in the meantime, we're looking to build our pilot plant. So we're hoping to process around 1,000 tons of carbon dioxide a year. Basically, 1,000 tons of carbon dioxide will be passed over the catalyst in a year. And the aim is that it will be a mobile pilot plant, so we can move it to different steel mills, try it with both DRI and blast furnace steel. Each steel mill is very slightly different, and the top gas that they emit will be slightly different. So we really want it to be movable, that we can try it in as many places as possible. And we're currently actually in conversation with quite a few different steel mills about hosting that pilot plant once it's up and running. And then kind of beyond that is kind of the demonstration scale. And we're looking at about the 20,000 tons of CO2 processing capacity, which is a relatively big unit. The thing with steel is the scale is so massive that you could have a plant making 5 million tons of steel a year. So therefore, 20,000 tons of carbon dioxide isn't particularly big, but on a kind of regular scale, actually 20,000 tons of carbon dioxide isn't insignificant. So we're just kind of using that as our stepping stone before we go to the really big scale that can actually have a big impact in the steel industry.
So get this right with these mobile units, prove the concept to, because you prove it to yourself, you've already done that, but you've got to convince people who own steel mills that they want to adopt it. So if you can prove it to them, are there incentives for them to want to adopt the sort of closed loop system rather than be emitting CO2? Are there other incentives outside of the fact that this is just good for the planet, good for industry?
Yeah, so obviously kind of the most common incentive is kind of carbon taxes in places that have them. Obviously, there's a benefit there, directly financial, to not emitting those emissions. In actual fact, even in countries without a carbon tax, we're finding that our kind of techno-economic analysis shows that we're actually cheaper and use less energy than existing steel mills. So in a blast furnace, the amount of kind of extra electricity we need to generate kind of any extra heat is less than the savings that you get from buying less coal or coke. So you actually end up with a negative cost of carbon abatement, which, as far as we're aware, we've never seen anywhere. We've seen that when we've kind of gone back to the steel mills with the updated findings, so that kind of came from a full process redesign. The reception was very different than when you're talking even $50 a ton is cheaper than kind of the EU carbon price at the moment, so you'd still benefit. But actually, when you're getting to negative costs, it's cheaper to decarbonize than not. And so, it's been very exciting.
And so there's a profit incentive or a bottom line incentive for businesses to do this.
Yeah,
which is great. So people should be queuing up really to take to say, please come and test with us.
Yeah, exactly. That negative cost is even when we account for the fact of the kind of capex to build the Perocycle equipment. So it's been very exciting.
Okay, yeah, very exciting. How long have you been going?
The idea was developed kind of as part of my PhD, kind of late 2021. Things obviously take a while. So the Perocycle as a spin out from the University of Birmingham was founded December 24. Then in June, we hired Grant Budge, who's our CEO, fantastic range of experience that was exactly what we needed. And then I came kind of back on board in October last year. So we're moving quickly. We want to move even faster. We want to get that pilot built so that people can start seeing it in the real world. So things are moving at pace.
And I think that moving at pace is absolutely right, because sometimes when people have fantastic ideas and startups and so on, it can take years to get them to even the point where you're talking about now, which is these kind of mobile live proof of concepts. Is that a way to put it?
Yeah.
And to get to that point can be a long road. Do you have help from people like Catalyst? Have you been working with those sorts of firms or government bodies, I guess? Innovation bodies, or are you? This has just been all organic, and you've just gone out there and done it.
Yeah, so we were lucky. We had some kind of startup funding from Anglo American, so that kind of helped get the business off the ground. We've been very lucky in the last couple of weeks that we've won an Innovate UK grant, so that will help us to kind of build our pilot plant. Had lots of support, still have lots of support from the University of Birmingham, and kind of my amazing PhD supervisor and his team are still working on the catalyst there. We're lucky to have support.
And the reception from people within the industry, you're finding that to be positive as well at the moment.
Yeah, and we've definitely noticed even in the last couple of weeks that actually we've got steel mills reaching out to us for the first time, rather than it being us going and knocking on doors and saying, can we tell you about our technology? We've actually finally had it kind of coming the other way. And we've recently been signed to do a feasibility assessment on a steel mill. So actually looking at their real world mill and exactly how it works and all the sources of heat and emissions that are at their mill, and actually showing how we would deploy kind of the Perocycle concept at their mill. And so we're looking to do kind of a few more of those so that we've got a wide range of kind of experience with different mill setups, because we think there's opportunity for integration than we've done so far. So at the moment, we're not touching kind of sources of waste heat outside of the top gas that contains the emissions. Whereas in a steel mill, there is lots of heat kind of everywhere. So we think there's more opportunity for integration that could actually bring those costs down even lower and bring the electricity consumption further down.
You did say when we started talking, you mentioned that, this is steel at the moment, but maybe there are other applications for this.
Yes.
Tell me more about the sort of other applications you're thinking about.
Yeah. So essentially it's any industry that produces emissions, kind of first of all, but ideally that uses a carbon source as a source of kind of carbon rather than just a fossil fuel as a source of energy. We've had a good look at nickel, and we think nickel's a really interesting application. See, the scale is smaller than steel, so it'd be slightly easier to build as kind of a next step between the demo and kind of full commercial steel unit. And actually, nickel can have up to 40 tons of carbon per ton of nickel produced, which is extraordinary. And I don't think I didn't know that before we had a look at it. So that one's a really exciting one. There's obviously other kind of non-ferrous metals where we still use kind of coal and coke or natural gas as a carbon source. There's also obviously the chemical sector. So at the moment we're using fossil fuels to produce carbon monoxide, because carbon monoxide is great as synthesis gas. It basically just means you can transform it into other chemicals. So that's definitely kind of an option. We also kind of see a point where, because it's cost effective to implement the system, even if a site didn't need all of the carbon monoxide itself, say it only needed a small part of what we produced, actually that carbon monoxide could be sold to another user who does need carbon monoxide, but maybe doesn't have such a good source of emissions. So we can kind of tag on to other kind of CCU or CCS options. And actually kind of on that CCS front, even on a steel mill, we wouldn't necessarily go from kind of 0 to 100% closed loop, we might go kind of 0 to 50. The emissions that are left actually end up being highly concentrated. So in a lot of the scenarios that we're modeling, we actually get over 90% carbon dioxide concentration of our kind of waste gas. And it kind of over 95% is what's typically kind of cited as requirements for transport and geological storage. So actually, we're essentially enabling CCS without any of the capture cost, because that's already been taken into account in the closed loop. We've just kind of made extra carbon dioxide that's highly purified.
We should clarify CCS, carbon capture and storage.
Yes.
Yes. But by making it more concentrated, then I imagine what's happening is you're making it easier to capture, as well as easier to store and easier to transport. There's no T in CCS, but transportation is another aspect of that.
And actually some early work has found that even if you took $50 a ton as the transport and storage cost, which is kind of, I think, relatively optimistic at the moment. But even so, the total cost of carbon abatement for all of the carbon in the steel mill would be something like $10 a ton. And if you've currently got carbon prices up at 70, 80, sometimes $90 a ton, that's a big, big cost saving. And you could get to 100% emission reduction kind of through a mix of a closed carbon loop plus that kind of carbon capture and storage of the remaining emissions.
I think there's another point that's really interesting when we talk about carbon capture and storage. I mean, I talked about transport. There's no T in CCS. There's also, I think, for many people, this idea that you capture carbon and then you store it somewhere and that's kind of it. Like you just inject it into old oil wells, or you put it somewhere in the ground, or you do something with it and then it's gone from the atmosphere and, hit hooray sort of thing. But actually you're saying, and I think this is an often overlooked point, that carbon dioxide that's been captured has a use commercially, right? It's not just something that, we capture it and, what do we do with it? We need to find some hole to put it in. It's actually, we capture it and there's a real commercial benefit to having captured it that can help us in our industries.
Yeah, exactly. And we find that the kind of highest efficiency, the lowest energy use comes from the systems where that carbon dioxide is converted to carbon monoxide and then completely reused in the system. And we're seeing that DRI, we think we could go kind of straight towards 100% swapping of natural gas for carbon monoxide. It's relatively easy because it's already a gas-based furnace. Swapping carbon monoxide and hydrogen for carbon monoxide is obviously relatively simple. On the blast furnace, it's slightly more complex because the coke provides a kind of structural role as well as an energy and carbon source role. So even if we can't get to 100% replacement of coke, and we think there's definitely work to do, and we're very lucky that we've set up an industry kind of steering committee with a few steel mills to try and work through those issues, because we can't redesign a blast furnace. We can't fix how it works. That's not quite in our remit. And they're the experts on their mills. But yeah, even if you couldn't get to 100%, let's say you did 50% reuse internally, you've still dramatically lowered the cost of kind of carbon capture, whether it's then used or stored somewhere else. By having that internal recycling, it just dramatically improves the economics of the system.
So there's the financial economics, but there's also the environmental economics. And that in both of those, you're improving the economics, the economic cycle. That has to be compelling, at least, for people to want to have a look at.
Yeah, and we're seeing an energy benefit as well. So because obviously burning a fossil fuel has never been 100% efficient, whether it's in a kind of power plant or within a furnace, we're actually seeing total energy consumption per ton of steel produced actually dropping by about 35%. And that's even accounting for kind of the extra electricity we would need to produce any heat that we need. Obviously, as I kind of said, we're expecting that there might be more sources of kind of heat that we can use on site to drop that further. But even where we're at currently, we're kind of a 35% decrease in total energy use. And actually, even if we compare with other kind of carbon dioxide splitting technologies, so we're the kind of thermochemical route, so change in temperature creates a chemical reaction. You've got electrochemical, which is obviously using electricity to split carbon dioxide. And then you've got kind of more the thermal route, such as with plasma. And we're seeing that kind of the plasma route is up about 5 kilowatt hours per kilogram of carbon monoxide produced. Thermochemically, the very best you could ever get, kind of the theoretical maximum efficiency would get you at 2.5 kilowatt hours per kilogram of carbon monoxide. We're seeing a system where we end up about 1.1 kilowatt hours per kilogram of carbon monoxide. So significantly lower than other kind of carbon dioxide splitting technologies that are out there currently.
And that has, particularly, I guess, for the electric splitting, a beneficial impact on grid drawdown.
Yes, yeah, exactly. Because we can use sources of heat as well as kind of using electricity to make heat. Yeah, total electricity consumption is significantly lower.
The economic arguments, it's compelling because it stacks up on different layers, depending on the type of furnace that you're looking at. Yeah, okay. And there could be uses for this across other different. It sounds to me like, in particularly, when refining different metals, especially.
Yeah, I think so, because they're typically such kind of high temperature processes, and they're using kind of coal as a source of kind of producing carbon monoxide to be a reducing agent. It's such an easy place to kind of fit in that, we think kind of the metals industry is kind of the first place we'll properly explore. We'll then also look at, I should have mentioned earlier, like kind of ceramics and cement. There could be some applications there. Basically anywhere where you've kind of got high temperatures, emissions, and ideally using a fossil fuel as a carbon source. But yeah, we'll see where we go from there. We're ambitious in our planning.
As you should be, right? There's that's how you create a successful business, which it sounds like you're doing very well. That ambition and that innovation, I think they're good bedfellows, let's say, or they go hand in hand anyway. Very often, what I've seen with other companies is people forget about the innovation and they just go straight for the ambition, or the ambition is kind of slightly forgotten and they get so locked up in innovation that they never really get to scale the business out. So if you're thinking about both, that's a really good way to do it, I think.
Yeah, thank you. Yeah, and we are always trying to look for ways to improve the process. So through different conversations, someone might ask a question and it will spark an idea, and we'll go and investigate if we could make that work. So we're constantly, trying to refine and improve it.
So you're going out, you're talking to lots of places at the moment. I imagine you're just very, very busy at the moment. There's a lot on for you guys, I guess. How big are you?
So at the moment, we're a very small team. So we're Grant, the CEO, and I, the CTO. We found a wonderful process engineer who will be kind of our head of process, who we're kind of just waiting to close on funding before we bring them in, but is very kindly doing some kind of consultancy work for us. So checking our models before we go out and tell people all these wonderful numbers and benefits. We've had them checked. And then we've got a wonderful kind of board level team. So we've recently brought on a new board member and a new board advisor who bring like lots of different experience in kind of financing carbon capture, and also in kind of the government end of carbon capture, to really expand the knowledge in the team. Once we close on funding, we are looking to hire a few more engineers to get us up and running with the pilot plant. We're purposefully keeping it relatively lean. So we found a wonderful international kind of engineering consultancy we should have some news about soon. So I can't yet say who they are, but who have a team of kind of 250 engineers that will be helping us with kind of the full design of the pilot and the demonstrator. That just means we don't have to be quite as big as this at this stage as if we were having to do it all in-house ourselves. Because trying to hire that many amazing people very quickly would be quite difficult.
Well, I think that's sensible. If you look behind me and look at the books on the shelves there, which probably everyone's got, but it's all about lean and how to flow business. And I'm a big believer that you can overhire. Then that can be a millstone around your neck, and then that can frustrate your ambitions. If you've got this announcement, which we shall look forward to hearing about, and when we get it, we'll put it underneath as well. We'll add it to the show notes. But if you've got someone that you're kind of contracting in to do that bit for you, that helps you keep it lean. Yeah, that helps de-risk it. And I think a company at your stage, just my tuppence, but that de-risking is really important, particularly given the importance of the mission that you've got, which I think is a brilliant mission, by the way. I think you're doing the right thing. That's what I'm trying to say.
Yeah, and we take that kind of de-risking quite seriously because we are a small team. We're aware of that. So part of kind of the equipment that Perocycle would bring to a mill is obviously you've got the thermochemical reactors where the CO2 splitting happens. But before that, we've kind of got gas separation technology. And at the moment, we've gone for kind of commercial gas separation, so it's called pressure swing absorption, or PSA, where there are giant PSAs that are built and are running in industry at the moment. And so by having that kind of existing proven gas separation technology kind of upstream and downstream of us, it de-risks that part of the process, so that kind of the only thing we're proving with the pilot is the actual thermochemical reactor. The rest of it's already been proven.
That's great, because it means that it gives you total ability to focus on that really important bit that you're doing and not get distracted by all of the other stuff that, you have to do, but you can actually get people to do for you. Your efforts, your mind, your talent, your brains that you have in the business, they're focused on the problem at hand.
Yeah, exactly. We're working quite closely with a couple of reactor design companies to really try and find who the best partner's going to be to build these reactors, knowing that we're starting off very small, but the scale grows pretty quickly as we kind of get to demo and then first of a kind. So trying to find those partners who can be with us for the long term and who can build on what we've learned from the pilot to do the demo better and then do the first of a kind better. And so that's, a lot of our time at the moment is trying to find those partners who will kind of be with us.
Very wise to build that capability in now as well, so you've got that growth expansion possibility. If people want to learn more about Perocycle, how do they do that? Where do they go? Is there like a website? Do you have, are there white papers? Is it, do they go on LinkedIn? What's the way to do that?
Yeah, so we've got a website, I think it's perocycle.com, and we've got a few, I think we've called it Zero Cycle, kind of like newslettery type things that deep dive on the topic and kind of how we see CC inline carbon capture and use working. So we've got quite a lot on the website. We're also on LinkedIn. We are aware that we need a marketing person to come and help us with the website, so please don't judge us on the website. But there's some information there. There's a contact email, so if anyone wants to know more, just drop us a line. We're always happy to have a chat.
I'll put the link to the website, albeit that you're asking people to forgive the state of it. I don't think that's going to be the issue, but I'll put a link to the website, and also we'll put a link to company page on LinkedIn. And also, if you give us the details of the newsletter, we'll be able to put that underneath, and then people can subscribe should they so wish. And I would encourage people to do so, because I think things like this are so important and so interesting. And, it's like we can live in the past and just keep reinvesting into things we've always done, or we can innovate and we can own the future. And I think this is part of that journey that we can go on. To me, it's like a second industrial revolution almost, because here's all this new technology. It's coming whether we like it or not. Let's grab it and own it and do something with it and make money from it. I'm not trying to sound like an evil capitalist, but
yeah, agreed. And we had a call yesterday where someone said, it's great that you're economic because the only way that decarbonisation is going to happen is if it saves money. And it's very sad that we're in that position, but it's true. And it does need to be economic. That needs to be a focus. As you say, I agree. We're in that new stage of, let's not see carbon dioxide as just a negative. Let's see the value that we can gain from it. It's an exciting time.
Yeah, absolutely. Harriet, it's been amazing talking to you. And maybe, I don't know, 6-9 months from now, we can check in and see where you've got to, and maybe give people a little update. I'd really like that.
That would be wonderful. We can bring you to the mobile pilot unit.
Oh yeah, we could do a live, not live, record it on site. So look, thank you very much again. I'm going to put those links, as I said, in the bottom for people. So do please go and click on those. They'll be under this recording. You can get there from by going to wickedproblems.fm if you're listening to this on Spotify or one of the other platforms. Harriet, thank you so much.
Thank you so much for having us. Really appreciate it.